Okay, yeah, I would like to talk about
Stefan Kraus.
Yes. Yeah, I will talk about two instruments. So I thought I structured maybe starting with an update on MIRC-X, what is the current status and what we're planning to do over the next few years. Then I'll go into some MIRC-X science that we want to target in the upcoming survey. And after that, switch over to Bifrost and what the status there is, and add some other science aspects that we can address with Bifrost on top of what we plan to do with MIRC-X. So yeah, on behalf of the whole MIRC-X team, I would like to give you an update, including, of course, the key Michigan team with John, Ben, Tyler, Jacob, Nora, and many new people joining here in Exeter just in the last half year. And let's see, does this work? Yeah, I won't go too much into the basic design of MIRC-X because it's also similar to what Ben showed yesterday for Mystic. So it's a fiber-fed instrument. Here was non-redundant arrangement in a weak groove, and then here separate photometric channels. So I think, as you saw in this meeting, MIRC-X is now really one of the workhorses of CHARA, with about 2/3 of the observing programs using MIRC-X and now also Mystic. So we saw 11 talks presenting MIRC-X results in the last few days, and in the meantime, the remote operation is also well established. So if you're observing, you can use the Atlanta remote observing machine, and this worked very well. That by the start of the pandemic, we had that mode already established, and so could keep observing. And in the meantime, you get MIRC-X and Mystic co-phased by default. So basically from this semester onwards, we always record H and K bands simultaneously. And also the recording of the data sequences is well synchronized and just works without overheads or significant time losses, despite using two instruments at the same time. And you can co-phase it basically at the beginning of the night with a 6 telescope simulator. That's our calibration source that is used for alignment and co-phasing, but then also optimize it later on during the observations. And you will also soon use MIRC-X for speaker as fringe tracker, which could be either in the current configuration where you have this all-in-one beam combination, or with a dedicated integrated optic chip that has been developed by the speaker team in Nice. And there's also a very exciting mode being developed by Ben Zetterholm aiming at polarization measurements. So basically, each of them mirrors along the path can add a phase on the Stoke vector to it, and so you need to characterize and be able to calibrate for these polarization effects. And in order to do that, we have a Wollaston where you can have your split polarization modes, as well as halfway plates that have now been mounted here on a motorized elevator mount. So you can with the press of a key lower these and then select the polarization angle you want to probe with this halfway plates. And the goal there is first to improve the visibility calibrations that you could get by accounting for the polarization, potentially to improve the closure phase accuracy for the hot Jupiter detection program, and ultimately also to search for polarimetric signals within the sign stars themselves, such as young stars, where this is a prediction that there could be dust signatures in the innermost AU. It could also maybe help the CHARA team to know which optics to focus on for recoating, because this kind of analysis also tells us what are the poorest mirrors along the path. And Ben has has taken here, for instance, calibrator measurements where you see visibility here overnight. And you see that there is a loss of contrast here among these calibrators. And he has a software tool where he simulates this Stokes vector phase for each individual mirrors here from M3 to M8, and then tries to reproduce such a signature with these polarization effects. And so it looks promising that some of this can be explained with this polarization effects. And if you then would fit these parameters, you could characterize the polarization properties of CHARA and make ultimately the science observations feasible. And what we have now coming up in the next half year or so are various upgrades that will be carried out by the Michigan and Exeter team working together, including the installation of a filter wheel, where we have already this filter wheel here in John's lab, and now want to install it at MIRC-X that one can switch the spectral mode during the night more efficiently without manual intervention. So other development will be to have new fibers that are better equalized than what we have at the moment in order to enable J and H-band observations also with 6 telescope mode. So the V-groove that we originally installed was optimized for H-band so that we're just properly just ideally sample in H-band. And so we will also change that sampling and therefore then have a 6 telescope J and H-band mode hopefully by default in a year or two. On top of that, there is the development to assist a speaker with a new injection module that will install a second set of off-axis paraboloids in order to have just a mirror to flip between the injection into the current all-in-one combiner or into the I/O speaker fringe tracker. And that's also going to be added on the table. Another upgrade for this year is a 6 telescope star tracker, STST, that will monitor and track the beams because at the moment you notice on timescales of minutes drifts. So we often have to do fiber maps again to re-optimize the injection. And with this STST and the C-Ray 2 camera that we're going to add, you can track this and don't have to do the fiber map so frequently as currently. Looking a bit further into the future, there is a program that we have with colleagues from INAV, and they designed for us VPHG gratings for a higher spectral resolution mode of MIRC-X. So the gratings up of 1000 and 5000 in J-band and also H-band for J and H. You can cover simultaneously with the 1000, for instance. And these VPHGs have a very high transmission, above 80%, and can therefore push the sensitivity for such high spectral resolution observations. That's they might be manufactured this year, and so this could arrive next year to have this higher sensitive gratings. And what would go very well with those new gratings, maybe then a year later, is that we plan for a major upgrade of the APD camera, where at the moment the read noise is extremely low. That was really the breakthrough of these APD detectors. However, there's still limitations with respect to the dark current and thermal background of 90 electrons per second per pixel. So if you want to use spectral resolution of 5000, this really becomes a problem. And so as part of the new Gaia Bifrost ERC project, we can potentially have the current camera upgraded with a new chip that has a reduced glow and also then an improved electronic timing and so the camera would need to be shipped back to France for a few months for that, but could then push the background down to a few electrons per second, and therefore really enables then the use of these high resolution spectral gratings for the object classes we're interested in. So this would be 2024, early 2024 likely. I also wanted to mention another issue from the last year, and that's a calibration problem that we see on S1 and S2. So, for instance, this plot here, you see just the visibility of calibrators plotted here in the size of the circles, and you would expect them to have around the same visibility independent of elevation, but it happens that here at an eastern direction and low elevations, there is a bias in the visibilities, resulting here in this low visibilities in that region. And so has been a lot of effort going into diagnosing this from the CHARA team and other colleagues. And so the idea was to find out whether this could be vibration on the MIRC-X table, vibration on the telescope, or vibration in the delay lines. And so different diagnostics point at the moment towards the cards, that there might be a problem with some cards when they are moving slowly. So when you're pointing east, essentially here you have this point here where the a card slows down and then reverses direction. And maybe there is a mechanical problem here in that region. So if you're a user of MIRC-X, that's something to watch out for, that you might have problems with baselines involving mainly S1 or potentially S2. But yeah, we can help with that. Then I wanted to cover very briefly the science. So I have to go quickly here. But we are starting a new survey in the near future, focused on Gaia binaries. And this is basically a survey where the idea is that in the northern hemisphere, we use MIRC-X. And in the southern hemisphere, we use Bifrost to do these kind of observations. And so the CHARA-focused program is basically summarized here, where one objective is to image binary formation and planet formation at early stages. So, for instance, here is an example from this GW Ori observations, where we measured the orbit with CHARA and then linked it to disk observations, or this kind of temporal changing structures in disks that we heard about earlier in the week. Is also aiming for this kind of dynamical perturbations to understand how these objects are forming. And then the other aspect to that is that you can also learn about the formation mechanism of planetary and stellar systems by studying the spin-orbit alignment. And there is, for instance, the hot Jupiter population, where you find that nearly half of the hot Jupiters are on oblique orbits. So they are strongly misaligned with respect to the rotation axis of the host star. And at the moment, with the classical approach of Frossiter-McLaughlin effect observations, you can only measure the spin-orbit alignment for very close transiting systems. But with interferometry, we can also get these the wide separation systems, and then learn, for instance, how planets or binaries are forming by populating this obliquity versus separation diagram, and then differentiating between disk fragmentation or cloud fragmentation processes, for instance, if we can get these spin orbit measurements for wide separation binaries with CHARA. That's a model prediction here, for instance. So there should be really a discernible change in the obliquity distribution depending on which of these processes is dominant. Here's an example where we used gravity, for instance, for that, to measure such a spin orbit alignment. But this tells you essentially the rotation axis of the star, if you can measure this photocenter displacements in absorption lines. But you need then some orbits to compare it to. And there is the third aspect, namely the statistics of orbits, where the upcoming Gaia Data Release 3 will be really a breakthrough. So there has been kind of a little teaser released by the Gaia team, showing here, for instance, the 8 Jupiter-mass planets. And if you then measure the stellar spin axis with interferometry of the host star, you can compare it to the orientation of the orbit of the planet or the binary, and really gets on the spin orbit alignments. And on top of that, the Gaia binaries are also very interesting for stellar astrophysics to measure dynamical masses and get high precision dynamical masses for a few hundred stars at CHARA likely, and at VLTI up to 6,000 stars is our estimation if we combine them in both hemispheres, and improve here the evolutionary tracks for stars over the whole HR diagram. So this kind of is an overview about what we're aiming for with MIRC-X in the next few years. Are there any questions on the MIRC-X part?
Let's thank Stefan for the first of his 2 talks here.
Is this about 15 minutes? Or,
Yeah.
Okay.
Yeah, you